So what I'm going to talk about today is some sort of, let's say, um, path of trying to fix a monolith. Basically, we have a monolith application, and we'll see some challenges on the way when the number of requests goes up. And we're going to try to solve that with some microservices. Um, First, a few things about me. So I'm an independent consultant. I live in London. I've been in the software industry for about 16 years, and in the past 5 years, I've been mostly writing web APIs, so working with microservices as well. Um, uh, Initially in Java, so based on Spring, and then later on, like in the last 3 years or so, I've been working mostly with Scala, with Akka HTTP, and in the past year, I've been also doing a bit of Spark, playing a bit with data processing on Spark and trying to scale it on Amazon AWS. Feel free to add me on LinkedIn, and I have on my GitHub account. I have also code from other presentations. The code I have a bunch of code for this one as well. So I have a project with the different solutions that we're going through. So if you can't follow during my talk, feel free to check it later. It's all on GitHub. I'm going to show you the link at the end. And yeah, so I have another project over there from my past talks. It's also about testing microservices if you're interested in that subject. So what's our scenario? Let's say we have a ticket booking website, and the current scenario would be, so a user comes to the website, and it will ask for the ticket availabilities, meaning that for a specific event, there could be different types of tickets. And also our API, because we're going to have an API for that, is going to return for each type of tickets the number of tickets that can be booked. After that, the user supposedly will choose in some UI what kind of tickets they want, and they're going to send a request to book the tickets. Once that is confirmed by the backend, then the user will be redirected to a payment gateway where they can pay for the tickets. So I'm showing that with a different color because that's not our system. And then once the payment is successful, then the user will come back to our website. And with the payment confirmation, we'll get a download link where they can download the tickets PDF. Okay. How now the challenge? So let's say that our manager comes in and says, you know, I got a contract and we have to sell the tickets for the U2 tour. And if you know, like the big bands and also the big artists, they have concerts on stadiums like that, and the tickets are getting sold in minutes. So how are we going to solve this? First of all, to show to show a bit the monolithic monolithic implementation that we'll start from. So basically, we have everything in the same JVM. We have a route. This is based on Akka HTTP. We have a route where we're defining what kind of endpoints we have. And then we'll have a service where we got all the implementation, like getting the tickets availabilities, and then once the user come back, we can book the tickets. And this is the payments part, which will, with a payment confirmation from the payment gateway, it will verify that everything is paid. And then getting the tickets, the actual tickets, like issuing ticket IDs, ticket numbers, and then creating the PDF. So the system is communicating with the payment gateway for the confirmation. So basically, we're going to see that in code. When the user comes back and says, "Okay, I'm confirming the payment," it will have to in the backend. It will have to confirm the payment is done. And supposedly with the database, where we have some sort of storage where we store the tickets and the available tickets. And also later on, maybe we'll store the user information. And some storage where when we're creating the PDF, suppose that we have, let's say, some branding images that are added on a ticket, so the ticket will be like on the fly generated for a specific person. Sometimes you can write on the ticket like who bought it, so that they can identify the entrance, and various things that you can add on the ticket. Now, our problem, as we'll see, so when our manager tells us, okay, we're going to sell you 2 tickets. Okay, what do we do first? Let's see how the system would be able to sustain that kind of load, right? So we start benchmarking our system, and we start easy with a 10 requests per second, just to to see how it is, and we identify. So this is how we split the request time. Basically, it starts with a request unmarshalling. I'm talking about here like the most. There are basically 3 endpoints, and we're talking about the request here that takes the longest, which is the PDF generation. We'll see. So the request unmarshalling, that's quite fast, and then communicating with the payment gateway. That takes a fair amount of time, but it's not that bad. And then some database operations, get tickets and save the tickets data. And then we notice that the biggest amount of time is spent on creating the actual print tickets. And then another short time for response marshalling and sending back to the UI, let's say. Now, going up, we notice that while the other parts, they scale pretty well, we notice that we have an increase in time while for the operation that actually creates the print ticket. And from 50% of the time of the request, now it hits up 75%. And we notice that increasing the number of requests per second, is not going anywhere faster. So actually it's going much worse. So just a second. Sorry. So I'm going to show you a bit the code that is behind the monolith part, and then we'll go for there. I'm not sure if you can see it. So this is the monolith root. So we have 3 endpoints. One is events ticket slash event ID. This is for getting the availabilities. Here is where we actually book the ticket. And here is when we come back from the payment gateway with a ticket done. Behind this route, the actual implementation is in a service, which is implementing based on futures. So all the functions are, yeah, they have dummy implementations, but basically you can see what kind of operations we have. And most of them, they return dummy data to simplify the presentation. And what I actually wanted to show you, so at the end of all this process, so here we save the payment confirmation, we get the tickets, and we save the ticket data. And in the end, we have a document ID that we use to return a download link. Now, the problem with this is that the total time of the request is influenced by the, let's say, the weakest link, right? The bottleneck in the system. So we're going to so what are the pros and what are the cons? So the pros is that it's very easy to start with a monolith, right? You don't need like fancy architecture. You don't need different systems. You don't need different deployment. While on the cons, as I said, like one bottleneck can affect the whole system. Yeah, since they are sitting in the same JVM, even if you kind of like have multiple nodes deployed, it's still that a JVM at a given point will have to accommodate with the resources all these steps, all these parts of the actual implementation. So imagine that if you would have, suppose like one of the operations needs like a huge amount of memory, then that's very difficult to scale, because if you need to increase that memory, you have to do it for all the nodes. It might affect the other parts in the system. And what I don't like about this implementation is that it's synchronous, meaning that the user is waiting for a download link. Now, the question is, can we change that? Do we really need to return the download link? So this, you know, in trying to somehow model the system in a different way, you have to step out a bit of the box and think, do I really need to do that? Another implementation would be moving from the JVM from the monolith in a single JVM way. Let's try to do it with Akka Actors, right? So we still stay in the same JVM for now. So we have the same route. We instead of a service implementing with futures, we put on actor. So basically, our service is an actor. The rest of the implementation is more or less the same. However, the advantage would be that, first of all, we can migrate to Akka cluster. We can distribute these actors. So we have one actor, but we could eventually split it in different actors. And then the cool part about that is that you can scale easier, adding nodes, and the actors can be sharded to more specific, to specialized nodes. Suppose I have that operation that I said that consumes a lot of memory, or maybe something that I don't know, consumes a lot of CPU. I could eventually shard those specific actors by type to different nodes, right? So this gives us a bit of a way to scale up. Now, what I don't like about this actor implementation is that we have the ask pattern. We have to use the ask pattern, and I'm going to show you right away. And when you have ask pattern, because from the route we're sending a message with ask pattern to the backend actors, and we're waiting for a response. So we need to define ask timeouts, which can be nasty at sometimes. And it's still synchronous. I'm going to show you now the code. So the root looks kind of similar. It's just for now, instead of calling the functions from the service, we're just using ask pattern and sending a command to that actor. Now, what's different from this implementation from the previous? Well, we started to use, because if you use actors, is more or less like you get to define your actions as commands, right? So we're using now case classes for our actions. Before we were just like calling a function with some arguments. Now we say, okay, I'm sending you this get available tickets command with the event ID, and I expect you to give me back also some data, right? So I find that more neat, because you encapsulate your all your parameters in a case class, and also this means that with this you can delay the actual calling. So you send this to an actor, and it doesn't have to happen now. It's when the actor can pick up that message, right? So it's the same for the others. So I have here book tickets that takes the a ticket type and quantity, and later on confirm payments, where I have basically the transaction key, some leads, which is the actual when we're booking the tickets, we get the lease that is valid for like 10 minutes. So we have to do the payment. And then the user details, so that we store that in the database, we put some info on the tickets, etc. Okay. And basically, our actor looks like this. So we have a sealed trait with all the commands that could be sent to this actor. And then inside, we can juggle a bit with the implementation. Right now, I'm using absolutely the same implementation, but notice that we kind of separated that a bit. So from here, I can define it in a different way quite easily. So I can split it maybe in different actors. So this allows us to refactor a bit the system in a different way. But as I said, I still don't like this because it's synchronous. So, well, the synchronous part comes from the fact that we're still returning the download link. So how about if we don't? Another way of splitting this. So as I said, we can with Akka clustering, we can basically scale up, and we can shard some actors on different nodes. But one way would be to extract some particular functionality in its own in its own REST API, right? So let's explore that a bit. So we have basically the same kind of functionality, except that this create PDF, we said, okay, this should be in a different system. I don't like it here. It's putting my system down. And this becomes just like a proxy for this other REST service. And notice that the supposedly slow storage that is kind of affecting our create PDF action was isolated with its own service, while our service still communicates with a database and the payment gateway system. Notice here that we need to create another route. We need to create a REST API. We need to stick to some API contract. And then we have the service here, and we will see how we do the implementation later on. So what are the pros and cons? Now this allows a more granular scaling on each microservice, because now we can say, okay, the front-end service needs this kind of hardware specifications, this amount of memory, this amount of CPUs, while the backend one, we say, it doesn't actually need that much CPU, but it needs more memory probably. Or we can define let's say a different hardware configuration, and also we can say now we need 2 nodes, but maybe tomorrow we need 4 nodes. But instead of scaling the whole system, because of a specific operation that needs more bandwidth, more processing power, then we can say, yeah, I'm not going to give more nodes to the whole system. The front-end system remains the same, while we can juggle a bit with the backend. Still synchronous, as I said, because the round trip of the call to that REST API, backend REST API, is going to still affect us on the response time. And what I don't like about this is that we just introduced some extra boilerplates that you have to maintain. So we define the backend API. We need to stick to that contract. We need to define that route. Let me show you the implementation to make it a bit more clear. So now it's not very clear, but here I have, so as opposed to this one where we had just one service, so we can see it, at least in as blurry as it is. But here we have the front end and the back end. We have 2 different services, right? And while the front end route looks more or less the same, so the backend route will look like this. So we have this API that will be called by the front end. So we implemented the call to the backend in the actual front-end service. So the route remains more or less the same. And then one of the actions, one of the safe PDF, as I said, is just the proxy for the backend REST API. Now, so another idea pops up, and it's how about if we forget about returning the download link, as I said from the beginning, and we take this slow operation, and we just do it on our own time. And instead of returning immediately a download link, we say, okay, we're going to send you an email where with the download link, and you can download it later. So imagine like all those like tens of thousands of people that are crazy to get a U2 ticket for the concert in 1 year from now. They can still book it. The system will be able to respond, but we're going to process this. We're going to create these PDF documents on our own time, allowing to scale easier, right? So in this scenario, in this implementation, so we still have the front-end service. We still, so instead of doing an API request to the backend service, now we just post the data to Kafka. But I mean, I took Kafka as an example, but you could use any message broker you would like. And then we still have like a second service, which is consuming the messages from the same message queue on Kafka, and it creates the PDF, and then it could also like send email and maybe save more stuff on the database, etc., etc. Now, the advantage in this case is that it still allows the granular scaling on each microservice, right? It is asynchronous, meaning that I'm just firing this command, and I don't wait for the response. So this means that I can immediately return to the user and say, okay, that's it. I confirmed it. You'll get the link in a few minutes. And then what I really, really like about this is that the programs are represented by data. And when you do that, so you, so when you, let's say, call a function, right, that's returns a future. This means that I'm starting to do the operation now, right? You give it the arguments and so on. But if you define the arguments as data, what you could do is you can postpone the actual execution of the command, right? And this allows you to send it to Kafka and let another service pick up on its own time and process it. There's one advantage for this as well, that Kafka is acting like a shock absorber. So imagine like in the first few minutes, like there are maybe 100,000 requests, right? And Kafka will, of course, configured properly, will allow you to store those events and consume them slower, at a slower pace, right? So it's absorbing this massive heat. And notice that I removed the API here, so no more boilerplate. We don't need to create that API contract, so no more boilerplate. It just goes to Kafka, subscribes, and it gets the data, right? So no more need to define a marshaller, and then all the crap, and then define a root. So this simplifies a bit our implementation, right? Now, of course, the cons is that you have an extra system that you have to set up, you have to deploy. It's Kafka. So maybe not everyone would like to start with this approach, but at least keep it in mind for later. So I can show you quickly. So what changed is that instead of doing the request to the backend API, we just use a Kafka producer to send messages on the orders topic, and we just return with order confirmed. But we can put more text in here, like, okay, you'll get an email, something like that. And yeah, basically, it's pretty easy implementation here. So you just have to define a record and define a Kafka producer, and I'm using Akka streams to publish to Kafka. And on the other side, I have the backend. Which is very simple. So on this side, I define a message handler function where actually it gets a message and it runs a future, and this does everything for me. It can create a PDF, and by defining a Kafka consumer, I pass it the message handler, which is called once I get a message, I can pass it to this function that will do whatever. So notice that it's quite simplistic. Like I've got rid of a lot of code in this backend service. So a few conclusions. As I said, programs as data it's really allowing you to postpone the execution, which means you can postpone a high load, right? So instead of processing 10,000 requests at a time, you can process, as slow as you can, right? So maybe instead of 10,000 requests per second, maybe you can process 5,000, right? So by putting these messages into Kafka, you can let your system cope with it at its own capacity, right? So yeah, Kafka allows you to absorb the loads, the peak loads, and then, I mean, you can start small. Like it doesn't mean that you have to write your application from the beginning. Okay, we're going to put Kafka here, and we're going to create this service and this and this and that. I don't think that solves the problems. I think you should start small, start monolithic, but keep it in mind and kind of see forward the moment when you have to extract them apart and rearrange the whole architecture, right? Um, Any questions? By the way, you can grab me if you don't do it now. You can grab me later. So feel free to ask me anything, whatever. So the code is available on GitHub. This project, but I have another project. It's called Akka Microservices, I think, where I it's the code from previous talks that I had about integration testing on microservices. So feel free to take a look. No questions? No, it wasn't necessarily the purpose of my talk. That was just to show, look, we identify the problem, and the problem is here. But of course, you should, ideally, you should do some performance testing. Depends on your production requirements, right? If you know that you're going to have a high load, then you want to see how is my system going to cope with that. And I used to work like maybe 4 years or 5 years ago on a project, and we used to, before every release that we did on our software, we used to do like a load test. And many times we could see like, oh, we have suddenly a bottleneck here, we have a red point, what happened? And then you would track it back and you would find that down to a commit when someone just added some, I don't know, synchronized or something like that. And you say, oh, why do you do this? So you realize that your system evolved in worse. And yeah, that's a good thing. We still have like 2-3 minutes. Yep. So, sorry, can you repeat again? So moving from monolith to microservices. Yeah, I mean, I guess I wouldn't talk about it right now, but no, I mean, software evolves, and I started actually my previous work at Expedia. We had an application, and at some point we realized, okay, this application doesn't scale anymore because we need a huge amount of memory. So we started to extract parts, and we extracted the basically a backend REST API. It's more like the example that I showed you. But that still didn't cut it in the end. So we ended up using a more approach, a more asynchronous approach, where we moved the data processing to Spark, and then Spark at some point was like posting messages in a message queue. So the initial monolith application that had that functionality inside would just get notifications. It was like, oh, this processing is done. Like, okay, then I can show it to the user. Well, the same. I'm giving you the same example because the REST part was a failure, and it was a failure in the sense that I was talking about the boilerplate, and you have like a route and an API, and you have like marshalling. That's another problem with this. It has to marshal, unmarshal that the data, and we came to a point where the data was so big and we couldn't shard it that you had to download something like a few hundred megabytes, and that was a failure. Like that's when our backend service started to go down, and we said, okay, we have to think about something else. Thank you. You can grab me at the speaker talk, at the speaker table.